This is the screencast for 10.2, example 5. Now, there's a few things here that I want to introduce you to that we're going to be going over in the next few screencasts. I'm going to introduce them all now and then pick apart each of these as we go through the examples. Velocity, acceleration, and speed. So, first of all, when it comes to vectors, suppose a particle moves along a smooth curve. So in other words, these vectors are letting our particle move off of the x-axis. How exciting! In the plane so that its position at any time t is x comma y, where x and y are differentiable functions. So the position vector, we're going to call r of t, is x of t comma y of t. So an expression that shows the horizontal position and an expression that shows the vertical position according to time t, or with respect to t. The particle's velocity vector then, look at that, is just the derivative of each expression in the position vector. Nice and straightforward. The particle's speed is going to be the magnitude, so the absolute value of v, or the length of the vector, which maybe not so much of a surprise. And then don't forget, speed is a scalar or a number, not a vector. The particle's acceleration vector is then yet another derivative, so the derivative of the horizontal velocity and then the derivative of the vertical velocity to show you an expression for the horizontal acceleration and the vertical acceleration. Finally, number 5, the particle's direction of motion is the direction vector v over the absolute value of v, and we'll look closer at that one in another example. So for example 5, doing calculus component-wise. So here's where we take vectors and we start to go into the calculus part of this. A, find the position vector of the particle at time t. Well, the position vector says a particle moves in the plane so that its position at any time t is greater than or equal to 0 is given by this point. So the vector from the origin to that point is going to be in vector form, and that's going to be the sine of t, comma, 1/2 t squared, or t squared over 2. So the velocity vector of the particle at time t then would be the change in x, comma, the change in y. So we're going to take the derivative of the x expression, so that's cosine of t, and then the derivative of the y expression, so that's just t. Find the acceleration of the particle at time t. So the acceleration is then again going to be the derivative of the x expression for velocity and then the derivative of the y expression for velocity. So we're going to describe the position and motion of the particle at time t equals 6. Basically look at what this tells us. First we can talk about the position of the particle. So the particle at time 6 is going to be the sine of 6, comma, 1/2 6 squared. So I took the position vector and I plugged in 6. Well, that's about sine of 6, comma, 18. Now, here's the thing though. That's not the position, that's the position vector. The actual position is a coordinate, sine of 6, comma, 18. So that's going to be that point right there that's symbolized on this graph. So this is a graph of the position of this particle. So the particle is no longer moving along the x-axis. Isn't this exciting? Alright, so then what about the velocity vector? Well, the velocity at time 6 is cosine of 6, comma, 6. So the velocity is like the change in x is the cosine of 6, might be meters per second, and then the vertical change would be 6 meters per second, something like that. That gives you both magnitude and direction. So it gives you both the speed and the direction the object is, the particle is going, just like we did with the airplane. Now the acceleration vector is going to be negative sine of 6, comma, 1. So the acceleration would be the, let's see, that would be the change in velocity, might be negative sine 6 meters per second squared horizontally, but then vertically would be 1 meter per second squared. The now try problem, number 31, says a particle travels in the plane with position vector r of t. Find A, the velocity vector, v of t, and B, the acceleration vector, a of t. Alright, so that's really nothing exciting, I guess. We'll find the velocity vector first. So we're going to take the derivative of the x expression, the horizontal motion expression for position. So that's going to be 2t and then plus 2 cosine of 2t. Don't forget the chain rule. Derivative of sine is cosine, derivative of 2t is 2. Then we'll take the derivative of the expression for the vertical position of this particle, and that's going to be 2t plus 2 sine of 2t. Now part B asks us for the acceleration vector, so we'll take the derivative of the velocity vector, that's 2, minus 4 sine of 2t, again using chain rule, and then comma 2 plus 4 cosine of 2t. So I have an expression for the velocity, the horizontal velocity versus the vertical velocity, and then the horizontal acceleration versus the vertical acceleration. Now, just to show you what the position will look like when I graph it, the path this particle is moving, I put in parametrics, the x-coordinate as the expression for position, the x expression, and then in the y equals, I put the y expression for the vertical position of the particle. I, guessed on the window, but found a good window. And here's where this particle is going. Very not symmetrical, just a random path determined by these two parameters for position.